Welcome to Tech Girl Kannada YouTube channel. LAI is a dimensionless quantity which indicates the total leaf area per unit ground area. For determining the canopy, the portion of a plant which is above the ground light, LAI plays an essential role. For sensing and transmitting the data from the deployment fields to the centralized units such as server and a cloud, different hardware components are used in the system. Commercial off-the-shelf COTS Telosby platform is used in the system. The Telosby modes are equipped with three types of sensors: temperature, humidity, light sensors with the help of optical and filter diffuser accessory. On the light sensors, the PAR is calculated to estimate the LAI. The system is based on the cluster concept. The Raspberry Pi is used as a cluster head which connects with 4 ground sensor modes. The Raspberry Pi is a tiny single board which works as a computer and is used to perform different operations in IoT. Humidity and wet plant intermittently cause attenuation to the system, which is minimized with the help of forward error coding (FEC) technique. The real deployment of the LAI assessment system involves various environmental and wildlife challenges. Therefore, for reliable data delivery, the authors take the redundant approach of using both wired and wireless connectivity. In the first deployment generation, USB power supply is used to power up the sensors and modes. The USB use it for configuring the sensor board and accessing the failure as per requirement. In this setup, a mechanical timer is used to switch off the sensor modes during the night. In the second deployment generation, the cluster is formed with wireless connectivity. The ground sensor modes consist of external antennas which help to communicate with the cluster head. A Raspberry Pi with long-term evolution LTE is used as a gateway in this system. Communication: the LAI system consists of multiple components such as WSN, IoT gateway, and IoT based network. All of these components are connected through wired or wireless links. The public land mobile network (PLMN) is used to establish connectivity between external IoT networks and the gateway. The data are analyzed and visualized with the help of Farm Management Information System (FMIS), which resides in the IoT-based infrastructure. Further, a prevalent data transport protocol (MQTT) is used in the system. MQTT is very high, lightweight, publish subscribe messaging protocol which is widely used for different IoT applications. The wireless LAN is used for connecting the cluster head with the gateway. The Telosby modes are based on the IEEE 802.15.4 wireless protocol. Software is an essential part of the system by which different operations of the system are executed. In order to operate the Telosby modes, Tiny OS and open source Loopar operating system is used. This OS is widely used for different WSN applications. Typically, in this system, the data acquired from the sensor node is stored and with timestamp and sequence number SN. For wired deployments, the first generation deployment, the sampling rate is used in 30 samples per hour. However, in the wireless deployment, the second generation, the sampling rate is significantly reduced to 6 sample hours. The tiny OS is capable of activating low power listening modes to the mode, which is used for switching a mode into low power mode during its idle state. In the ground sensor, telescope modes broadcast the data frame and the cluster head Raspberry Pi receives it. This received data is transmitted to the gateway. Besides acquiring the ground sensor data, the Raspberry Pi works as the cluster head. In this system, the cluster head can reboot any affected ground sensor node automatically. IoT architecture. The MQTT broker runs in the internet server of the system. This broker is responsible for receiving the data from the WSN. In the system, the graphical user interface GUI is built using an Apache server. The visualization of the data is preferred at the server itself. Further, when a sensor fails, the sensor informs the users. The server can provide different system related information to the smartphone of the registered user. Smart irrigation management system. Here you can see in precision agriculture, the regular monitoring of different agricultural parameters such as water level, soil moisture, fertilizers, and soil temperatures are essential. For monitoring agricultural parameters, a farmer needs to go to his or her field and collect the data. Excess water supply in the agricultural field can damage the crops. On the other hand, the insufficient water supply in the agriculture also affects the healthy growth of crops. Efficient and optimized water supply in the agricultural field is essential. This case study highlights the prototype of an irrigation management system developed at the Indian Institute of Technology, Kharagpur, funded by Government of India. The primary objective of the system is to provide a web-based platform to the farmer for managing the water supply of an irrigated agricultural field. The system capable of providing a farmer-friendly interface by which the field condition can be monitored. With the help of this system, a farmer can take the necessary decision for the agricultural field based on the analysis of the data. The farmer need not to worry about the complex background architecture of the system. It is an affordable solution for the farmers to access the agricultural field data easily and remotely. Architecture. The architecture of this system consists of 3 layers: sensing and actuating layer, remote processing and service layer, application layer. These layers perform dedicated tasks depending on the requirements of the system. Figure 12.5 depicts the architecture of the system. The detailed functionalities of the different layers of this system are as follows. Here you can see the diagram. This is the cluster head, processing board, soil moisture sensor, water level sensor, server. Architecture: smart irrigation management system. Sensing and actuating layer. This layer deals with the different physical devices such as sensor nodes, actuators, and communication modules in the system. A specially designed sensor node works as a cluster head to collect data from some other sensor nodes which are deployed on the field for sensing the value of soil moisture and water level. A cluster head is equipped with 2 communication modules: ZigBee, IEEE 802.15.4, and General Packet Radio Service GPRS. The communication between the deployed sensor nodes and the cluster head takes place with the help of ZigBee. The cluster head uses the GPRS to transfer data to the remote server. An electrically erasable programmable read-only memory EEPROM integrated with the cluster head stores a predefined threshold value of water levels and soil moisture. The sensor value of the deployed sensor node drops below this predefined threshold value, a solenoid pump activates to start irrigation process. Sensor value of the deployed sensor node drops below this predefined threshold value, a solenoid pump activates to start irrigation process in this system. Standard EC05 soil moisture sensor is used along with the water level sensor, which is specifically designed and developed for this project. Water level sensor is shown in the figures 12.6. A. Processing and service layer. This layer acts as the intermediate layer, the sensing and actuating layer, and the application layer. The sensor and process data is stored in the server for future use. Moreover, these data are accessible at any time from any remote location by authorized users, depending on the sensor values from the deployed sensor nodes and the pump actuates to irrigate the field. The processing board, as depicted in the figure 12.6, is developed for the project. This is water level sensor and the processing board, water level sensor and the processing board. Application layer. The farmer can access the status of the pump, whether it is switched on or off, and the value of the different soil parameters from his or her cell phone. This information is accessible with the help of the integrated GSM facility of the farmer's cell phone. An LED array indicator and LCD system is installed in the farmer's house. Using the LCD and LED, a farmer can easily track the condition of his respective fields. Apart from this mechanism, a farmer can manually access field information with the help of a web-based application. The farmer can control the pump using his or her cell phone from the remote location. Deployment. The system has been deployed and experimented in 2 agricultural fields. An agricultural field at the Indian Institute of Technology, Kharagpur, IIT Kharagpur, India. Benapur, a village near IIT Kharagpur, India. Both the agricultural fields were divided into 10 equal sub-big fields of 3 into 3 m2. In order to examine the performance, the system was deployed at over 4 subfields. Each of these subfields consists of solenoid valve, a water level sensor, and a soil moisture sensor, along with a processing board. On the other hand, the remaining 6 subfields were irrigated through a manual convention irrigation process. The comparison analysis between these 6 and 4 fields summarizely reports that the designed system performance is superior to conventional manual process of irrigation. Next, we are entering into the vehicular IoT. Figure 13.1 represents the simple architecture of a vehicular IoT system. The architecture of vehicular IoT is divided into 3 sub-layers, that is, device, fog, and cloud. Device contains the vehicle internal environment sensing, external environment sensing, data collection and sharing, event triggering. Fog, lower end processing, small scale analytics, short term storage, decision making near devices. Cloud, higher end processing, heavy end analytics, long term storage, decision making. Now we are getting into the device. The device layer is the bottommost layer, which consists of a basic infrastructure of the scenario of the connected vehicle. This layer includes the vehicles and roadside units, RSU. These vehicles contain certain sensors which gather the internal information of the vehicles. On the other hand, the RSU works as a local centralized unit that manages the data from the vehicles. Fog in vehicular IoT systems, fast decision making is pertinent to avoid accidents and traffic mismanagement. In such situations, fog computing plays a crucial role by providing decisions to real time much nearer to the devices. Consequently, the fog layer helps to minimize data transmission time in a vehicular IoT system. Cloud fog computing handles the data processing near the devices to take decisions instantaneously. However, for the processing of huge data for computing in enough, therefore, in such a situation, cloud computing is used. In a vehicular IoT system, cloud computing helps to handle processes that involve a huge amount of data. For long-term storage, cloud computing is used as a scalable resource in vehicular IoT systems. This is the components of vehicular IoT. Modern cars come equipped with different types of sensors and electronic components. These sensors sense the internal environment of the car and transmit the sensor data to the processor on road. Deployed sensors sense the external environment and transmit the sensor data to centralized processor. Therefore, thereafter, based on the requirement, the processor delivers this sensor data to fog or cloud to perform necessary functions. These processes seem to be simple, but practically several components along with their challenges are involved in a vehicular IoT system. Figure 13.2 depicts the components required for vehicular IoT systems. Components of vehicular IoT. Vehicular IoT. It's wireless connectivity, sensors, and analytics, cloud, and for computing, roadside units, satellites. Vehicular IoT. Components of vehicular IoT. Sensor and vehicular IoT sensors monitor different environmental conditions and help to make the system more economical, efficient, and robust. Traditionally, two types of sensors, internal and external, are used for a vehicular IoT system. Internal, these type of sensors are placed within the vehicle. The sensors are typically used to sense parameters that are directly associated with the vehicle. Along with the sensor, the vehicles are equipped with the different electronic components such as processing boards and actuators. The internal sensors in a vehicle are connected with a processor board to which they transmit the sensor data. Further, the sense data are processed by the board to take certain predefined actions. A few examples of internal sensors are GPS, fuel gauge, and ultrasonic sensors, proximity sensors, accelerometer, pressure sensor, and temperature sensor. External sources quantify information of the environment outside the vehicle. For example, there are sensors used in smart traffic systems that are capable of sensing vacant parking lots in design parking area. The still images and videos are processed further either in the fog or in the cloud layer to take certain pre-programmed actions. As an example, camera sensor can capture the image of the license plate of an overspeeding vehicle. At a traffic signal, the image can be processed to identify the owner of the vehicle to charge a certain amount of fine. Similarly, temperature, rainfall, and light sensors are also used in vehicular IoT infrastructure. Satellite and vehicular IoT system, automatic vehicle tracking and crash detection are among the important available features. Satellites help the system to track vehicles and detect on-road crashes. The satellite imaging is also useful for detecting on-road congestions and roadblocks. Wireless connectivity, as vehicular IoT deals with the connected vehicles, communication is an important enabling component. For For taking any action or making decisions, the collected data from internal and external sensors need processing. For transmitting the sensor data from multiple sensors, need processing. For transmitting the sensor data from multiple sensors, RSU, roadside units, and from RSUs to a cloud connectivity plays an indispensable role. Moreover, in the vehicular IoT scenario, the high mobility of the vehicles necessitates the connectivities type to be wireless for practical and real-time data transmission. Different communication technologies such as Wi-Fi, Bluetooth, and GSM are common in vehicular IoT systems. Roadside unit RSU. RSU is a static entity that works collaboratively with internal and external sensors. Typically, the RSUs are equipped with sensors and communication units and fog devices. Vehicular IoT system deals with time critical applications which need to be taken decisions in real time. In such a situation, the fog devices attached to the RSUs process the sensor data and take necessary action promptly. If a vehicular system involves heavy computation, the RSU transmits the sensor data to the cloud, and sometimes these RSUs also work as an intermediate communication agent between two vehicles. Cloud and fog computing. In vehicular IoT systems, fog computing handles the lightweight process geographically closer to the vehicles than the cloud. Consequently, for faster decision making, fog computing is used in vehicular IoT systems. However, for heavy weight process, fog computing may not be suitable option. In such a situation, cloud computing is more adept for vehicular IoT system. Cloud computing provides more scalability of the resources as compared to fog computing. Therefore, the choice of the application of fog and cloud computing depends on the situation. For example, the location and extent of the short-known road congestion from a certain location can be determined by fog computing. With the help of sensor data, congestion information can be shared by RSU among others on the road vehicles, thereby suggesting that they avoid the congestion roads. On the other hand, for determining regular on-road congestion, predictions are typically handled with the help of cloud computing. For the regular congestion prediction, the cloud end needs to access a huge amount of instantaneous data as well as historical data for the stretch of road spanning back a few months or 2 years. Analytics. Similar to different IoT applications domains, in vehicular IoT, analytics is a crucial component. Vehicular IoT systems can be made to predict different dynamic static conditions using analytics. For example, strong data analytics is required to predict on-road traffic conditions that may occur at a location after an hour. Advantages of vehicular IoT. The typical advantages of IoT architecture directly impact the domain of connected vehicular systems. Therefore, the advantages of the IoT are inherently included the vehicular IoT environments. The few selected advantages of vehicular IoT are depicted in the figure 13.3. Easy tracking. The typical advantages of IoT architectures directly impact the domain of connected vehicular systems. Therefore, the advantages of IoT are inherently included in vehicular IoT environments. A few selected advantages of vehicular IoT are depicted in figure 13.3. Easy tracking. The tracking of the vehicles is an essential part of vehicular IoT. Moreover, the system must know from which location and which vehicle the system is receiving the information. In a vehicular IoT system, the tracking of vehicles is straightforward. The system can collect the information at a remote location. Fast decision making. Most of the decisions in the connected vehicle environment are time critical. Therefore, for such an application, fast and active decision making are pertinent for avoiding accidents. In the vehicular IoT environment, cloud and fog computing help to make fast decisions with the data received from the sensor based devices. Connected vehicles. Vehicular IoT system provides an opportunity to remain connected and share information among different vehicles. Easy management. Since vehicular IoT systems consist of different types of sensors and communication unit, processing devices, and GPS, the management of vehicles becomes easy. The connectivity among different components in a vehicular IoT enables systems to track every activity in and around the vehicle. Further, the IoT infrastructure helps in managing the huge number of users located at different geographical coordinates. Safety is one of the most important advantages of a vehicular IoT system. With easy management of the system, both the internal and external sensors placed at different locations play an important role in providing safety to the vehicle, its occupants, as well as the people around it. Record. Storing different data related to the transportation system is an essential component of a vehicular IoT. The record may be of any form, such as video footage, still images, and documentation. By taking advantage of cloud and fog computing architecture, the vehicular IoT system keep all the required record in its database. Easy tracking, fast decision making, connected vehicle, record safety, easy management. Crime assistant in a smart IoT transportation system highlights a fog framework for intelligent public safety in vehicular environment. Fog FISWAR. The primary aim of the system is to ensure smart transportation safety (STS) in public bus services. The system works through the following three steps. The vehicle is equipped with a smart surveillance system which is capable of executing video processing, detecting criminal activity in the real time. A fog computing architecture works as the mediator between a vehicle and a police vehicle. Mobile application is used to report the crime to nearby police agent. Architecture. The architecture of a fog FISWAR consists of different IoT components. Moreover, the developers utilize the advantages of low latency fog computing architecture for designing their system. Fog FISWAR is based on the three-tiered architecture as shown in figure 13.4. We will discuss each of the tiers as follows. Tier 1, Tier 2, Tier 3. Tier 1 image processor, event dispatcher, image processor, crime definition downloader, crime definition storage, algorithm launcher, event dispatcher, event notification, data gatherer, virtual sensor interface. Event dispatcher, event notification, data gatherer, virtual sensor interface. Tier 2 target object training, notification factory. Tier 3 Crime Assistant Unit. Architecture of fog phosphor. Tier 1 in vehicle phosphor. STS fog in this system component. Fog node is placed for detecting criminal activities. This tier accumulates the real sensor data from within the vehicle and process it to detect possible criminal activities inside the vehicle. Further, this tier is responsible for creating crime level metadata and transferring the required information to the next tier. For performing all the activities, Tier 1 consists of two subsystems: image processing, event dispatcher. Image processing. The image processor inside the Tier 1 is a potent component which has a capability similar to the human eye for detecting criminal activities. Developers of the system used to deep learning based approach for enabling image processing technique in the processor to implement fog computing architecture in a vehicle. The Raspberry Pi 3 processor board is used, which is equipped with a high quality camera. Further, this architecture uses template matching and correlation to detect the presence of dangerous articles such as pistol or knife in the sub image of a video frame. Typically, the image process stores a set of crime objects templates and the phosphor STS for infrastructure, which is present in tier 2 of the system. The image processor is divided into the following three parts. That is crime definition downloader. This component periodically checks the presence of a new crime object template definitions in the phosphor STS frog infrastructure. If a new crime object template is available, it is stored locally. Crime definition storage. In order to use template matching, the crime object template definition is required to be stored in the system. The crime definition storage is used to store all the possible crime object template definitions. Algorithm launcher. The component initiates the instances of the registered algorithm in order to match the template with a video captured by the camera attached in the vehicle. If a crime object is matched with a video, criminal activity is confirmed. Event dispatcher. This is another key component of the Tier 1. The event dispatcher is responsible for accumulating the data sensed from the vehicles and image processor. After the successful detection of the criminal activity, the image is sent to the fog phosphor STS fog infrastructure. The components of the event dispatcher are as follows. Event notifier. It transfers the data to the fog phosphor STS fog infrastructure after receiving it from the attached sensor nodes in the vehicle. Data gatherer. This is an intermediate component between the event notifier and the physical sensor. It helps to gather sensor data. Virtual sensor interface. Multiple sensors that sense data from different locations of the vehicle are present in the system. The virtual sensor interface helps to maintain a particular procedure to gather data. The KISS component cooperates to register the sensors in the system. Tier 2 phosphor STS fog infrastructure. Tier 2 works on the top of the fog architecture. Primarily, this tier has three responsibilities: keep updating the new object, template definitions, classifying events, and finding the most suitable police vehicle to notify the event. Phosphor STS fog infrastructure is divided into two subcomponents: targeted object training. Practically, there are different types of crime objects. The system needs to be up to date regarding all crime objects. This subcomponent of the Tier 2 is responsible for creating, updating, and storing the crime object definition. The algorithm launcher uses these definitions in tier 1 for the template matching process. The template definition includes different features of the crime object such as color, gradient, shape, format. The new object definition is stored in the definition database. The database requires to be updated based on the availability of the new template definitions. Notification factory. The subcomponent receives notification about the events in a different vehicle with the installed system. Further, this component receives and validates the event. In order to handle multiple events, it maintains a queue. Tier 3 consists of mobile applications that are executed on the user's devices. Application helps a user who witnesses a crime to notify the police. Thank you for watching. Do like, share, and subscribe to my channel.